Então, logo depois da palestra da Adriana, o Ricardo vai mostrar um slide sobre esse evento. Então, Adriana, obrigado.
Okay, well, I was told I should speak in English, right? Because not everyone knows Portuguese. Unfortunately, I didn't know that before I arrived, so the slides are in Portuguese, but the plots, which are the important parts, you'll be able to read. So exoplanets, atmospheres, and habitability. So introduction, first of all, how do we detect exoplanets are planets outside our solar system. And how do we detect exoplanets? There are actually many ways to detect them. I'm not going to go into them. I'm only going to talk about transits, which are the most select way to detect exoplanets. And that was as of yesterday, 5,667 exoplanets confirmed. And about 70% of those were discovered by the transit method. And what is the transit method? At the planet passes in front of the star, where you're observing from Earth, we see a slight decrease in the brightness of the star, really small. For the biggest planet, Jupiter-sized planet, it's about 1%. And for an Earth-sized transit across the solar like star, it would be 0.01%. So it's really tiny. But the important thing is that it is a signal and it is detected. It can be detected. And of course, the major discoverer of planets was the Kepler satellite, which is not in operation anymore. But there's TESS, which is its successor. Okay, and what has it discovered? Discovered was your histogram of the biggest planet in the Jupiter size for Earth, Neptune and Jupiter sizes. And what you can see from the histograms that the vast majority of planets have a radius between 2 and 3 Earth radii. And of course, we don't have any equivalent planet in our solar system. So that was a big surprise that the most common planet in our galaxy is something that we do not have in our solar system.
So is that a bias, an observational bias that you have already?
No,
it's not.
Well, okay, it might be an observational bias towards small planets.
Yes.
But I mean, we can detect planets down to the size of Mars or smaller. So of course, not all of them, but so it might continue to grow. But nevertheless, we discovered that there is this huge population of planets that we know nothing.
But the sheer observation is not corrected by any observational factor. By any observational bias. It's the sheer observation.
Yes. Yes, you see, what I didn't say was in the previous slide was that the depth of the transit is proportional to the ratio of the area of the planet to the area of the star. So if we know the stellar radius, we will know the planet radius.
We didn't know that.
Yes, I think it was just one planet that was discovered from X-ray observations in another galaxy, but all those about 5,600 planets are within the Milky Way. So what kind of planets did we discover? First of all, of course, that was due to observational bias. Hot Jupiters. What are hot Jupiters? Those were the first planets discovered. A hot Jupiter, 51XB, is a hot Jupiter that, Michel Mayor and Didier Queloz were awarded the Nobel Prize of Physics in 2019 because of this discovery. Jupiter is a planet the size of Jupiter, but it's very close to its host star. So it's really hot, like temperatures of about 2,000, 3,000, at the top of the Kelvin, at the top of the atmosphere. And then those most common planets, the mini Neptunes and the super Earth, which I'm going to talk about next. And then what I find most interesting, the rogue planets, that's what they're called in English. And they are planets which do not orbit any star. They're just free floating planets within our galaxy. So Jupiter, again, this is a observational bias. The first planet is yes.
Oh, that's where. Here is from.
Yes, that is the main theory, but I'm going to get there. Yeah, I'm going to get there. So Jupiter's bias of discovery, because of course, the depth, the transit depth is going to be large. First of all, they were first discovered not from transits, but from radial velocity. And again, radial velocity also because the pull of the gravitational pull of the exoplanet on the star will make it more. And so you can detect the radial velocity shifts in the elements of the atmosphere of the star. But now we know that these are only 1% of the planet. And they are giant, Jupiter, with a mass larger than Earth mass. But they're very, very close to their star. So this is one astronomical unit is the average distance between the Earth and the Sun. So these planets are much closer to their star than Mercury is to our Sun. Of course, they were formed beyond the ice line that is, about the position of where Jupiter is or beyond, and then they migrated spiraling towards the star. So that's known as planet migration.
How they migrate, and tell us, I'm gonna tell us about the migration. Okay, let's just
Because I wanted to talk about my research, so I mean, I couldn't have even exchange slides. I think the one that I gave you passed. Okay, so Neptune, so we get teeny. Well, some people are coined this, but some people call them that. So the planets with masses between, remember, Jupiter is above 100 Earth masses, here between 5 and 10. These are the radii, Earth masses, and they have low density, so they are in fact gases, not giants. They're mainly composed of an atmosphere, composed of hydrogen and helium, just like the giant planets that we know here in the solar system, Jupiter, Saturn, Neptune, and Uranus. And again, no equivalent in the solar system. Then super Earth, there are planets with masses between 1 and 5 Earth masses, radii between 1 and 2 Earth masses, and they are rocky. Okay, so they are terrestrial planets, but with a much larger mass than Earth. And so they, of course, we don't know, but we speculate that how they would be, because of course the stronger gravity would make all the geological mountains and valleys much the mountains would be much lower because of the pull of the gravity. I mean, we know that in our solar system, the largest volcano is in Mars, right? Because Mars has a lower gravity than Earth. But anyway, so if they had like an ocean, so they would be completely covered in water. That's why sometimes knowing if they were in the habitable zone of the star where we could have water in liquid form, their surface would be completely covered by an ocean, just because there won't be any land mass high enough, like to form continents like we know here on Earth. And again, no equivalent in the solar system. And then the rogue planets. Okay, again, planets with no that do not orbit around the star. They are, of course, dark, because a planet, it emits in the infrared, but in the visible, it just reflects the light of its star. And they're detected again in the infrared, or the first ones were discovered by gravitational lensing. And I know you all know what that is. So you have the normal lens by the planet, and if this lensing planet has a planet of the normal lens of the star, and if this star has an orbiting planet, then the planet will act as a micro lens. And the good thing is that if you have the precise measurements of the mass, they usually giant planets, of course, giant gaseous planet, gas giants. But of course, this is most likely bias detection because we cannot detect the smaller ones. And what the estimate is that there are more planets of this type in the galaxy than there are stars. So we're talking about 200 to 400 billion planets of the sky, which are just floating through the Milky Way. And they are, probably the result of dynamical interaction with other gas giants in the planetary disk when all the planets were forming together with the star in the center of the nebula. Probably something due to the vibration, like of a Jupiter going to become a hot Jupiter. They were ejected from their planetary system. And of course, if you can eject a big giant gas planet, then you can also eject a light planet. So you probably have all sorts of planets just free floating. And I'm just one interesting thing here, because I'm going to talk about habitability. I'm not going to talk about this anymore, but one interesting thing is just if these planets were ejected, probably the planets if they had moons, the moons were ejected with it. Like just like Uranus, I don't know if you know that Uranus, it's tilted on its line. So it revolves around the sun. And its moons and rings are all also perpendicular to the ecliptic plane. So here's Uranus, and then all the moons go like this, and there's a very faint ring, which is also tilted, like the satellites and the rings, they retain their original position within the stellar equator, the planetary equator. So maybe one of these rogue planets, they also have satellites. And here in the solar system right now, the most probable candidates for finding life, it's not Mars anymore. It is the icy moons of Jupiter, Saturn, Europa, Enceladus, and Ganymedes, because they have a crust of ice, and due to the tidal heating, gravitational tidal heating, due to the proximity of a giant planet close to it, which of course makes the tides, of course it's within the planet, right? So the rock before it melts whatever ice. So if it was just supposed to be a crust of ice, like a large crust of ice, then there's probably an ocean, liquid ocean, like below this crust of ice. And that in Enceladus, when the Higgins flew over it, it detected, like things which are much like what we have here on Earth, like geysers, like the composition. Okay, so this
is something that we should expect from all planetary systems. I mean, the projection of planets that were found there.
Yes.
Are there specific conditions also?
I don't work with celestial mechanics, so I'm not the best person for you to ask that. But within the estimate of like more planets than stars.
Yes, exactly.
Yes.
Mm-hmm.
Another question.
So there's not a simple star there. It's not possible to detect the reality.
No.
So what's the best number? Which has
Yes.
Okay.
I guess like the gravitational lensing effect. Just happens by chance, and it's just once in a lifetime. And the first plot that I showed you about planet radii, if we zoom in on small planets, the solar Earth and the mini Neptunes, what we see is that there is a gap. It's not, like a Gaussian-like function like this or any other kind of distribution. It has a peak. It actually it's double peaked with a gap in between. That's known because due to the starboard photon, it's known as photon gap, and it's around 1.8 Earth radii. And yes. And we always say that office, but I did the only concern that because that's the way that it is at more planets is progress and that will give you the radius. Of course, the radial velocity it's a much smaller percentage of planets where we can do that. The radial velocity more like the ships in the storm. So that's why. And of course, but there are many planets where we have both. 2,000 planets where we have both. And for those, we know the density for sure. So we know it's gaseous or terrestrial. And the main explanation now is that, first of all, the planets were being Neptunians, and then due to the interaction with the star, basically through photoevaporation, the ultraviolet flux from the star evaporated their atmosphere, and so we were left with a bare core, which is terrestrial, which is rock. And so what we see is super Earth. So super Earth are bare, bald, if you wish, Neptune. The estimate is about 15 to 20 provinces rocky. So most of it is just the atmosphere. Okay, now that was the introduction. So now going into habitability. So what is the habitable zone of the star? The habitable zone of the star is that region that is not, if a planet is within it, it's not too close to the star that the temperature is higher than 100 degrees centigrade and all the water will evaporate, and not too far away that the temperature will fall to 0, which will freeze all the water. So, for instance, like the sunlight star, it's this green zone where the Earth is, and maybe Mars and all that will be. And then, of course, if the star is cooler, then there is less flux, so the temperature will be lower, will be smaller. So the habitable zone shrinks in closer to the star. And the opposite for hotter stars, the habitable zone has to be further away. Of course, that is like let's say a first order effect. What would the temperature of terrestrial planet be if depending on the stellar mass or stellar flux? But of course, it's not just that. It's not just the surface that the planet has to be Earth terrestrial, has to be rocky, and it has to have a temperature like for liquid water on water to be liquid on its surface. But we also want it to be stable for about 1 billion years, because we know that the first records of life here on Earth occurred at around 700 million years, or almost 1 billion years. So for life to emerge and maintain and grow here on Earth, we needed at least, like 1 billion years of peace and quiet. Of course, not only that, we have geological activity, an atmosphere made of CO2 and water and nitrogen, a magnetic field to prevent us, to protect us from cosmic rays, and climate stability. It's with the tilted axis, rotation axis of the planet, and resistance to gas transfer is like
Why geological activities?
Well, because that's what the geological activity is, what made the carbon this year to cycle. So all the planets, when they initially formed, they're formed with the material that is in the nebula, that is basically hydrogen, some helium. So all primordial atmospheric planets, be them gas or terrestrial, will be hydrogen, mainly hydrogen. But of course, hydrogen is a very light particle, and it's easy to escape from small planets. So the atmosphere that we have now is secondary, and it was formed from volcanism, basically from volcanism. So we wanted to have this composition in the atmosphere. We need that, and not only that, but also to have kind of greenhouse effect. and all that. And so you don't want too much carbon in the atmosphere, and you want too little carbon in the atmosphere. CO, not carbon, I mean CO2. So the geological cycle helps with that. Okay. Oh, so here is, like there is the conservative estimate, then an optimistic estimate. This is just, and of course, this changes with time because we know that the star evolves, and as the star evolves, it gets hotter. So habitable zone will move outwards. And how do we detect life? So basically, I don't do it, that's astrobiology. So what people are trying to do is you can look for global signs of civilization, like changes in the atmosphere or in the magnetic field. Of course, the spectroscopy, you look for the basic molecules of life. And basically what we're looking at is large quantities of oxygen. Okay, you can have all oxygen is in the universe. I mean, it's in the galaxy. But for instance, in a large amount like it is on Earth, like about 20% of our atmosphere, that's not, that was produced by life. So that's one thing that we can look for. And then observations for distant look from the Galileo probe show that oxygen and methane in equilibrium can only be possible with the presence of light. And so here you can look at detection of oxygen and a triple detection of carbon dioxide, water, and ozone. Here is a list of possible habitable planets. This is updated a little bit from 2018, and it's from the University of Puerto Rico. And what you can see here's the gold zone. Planets that are too far away from their star, planets that are too close, so they're hot. And then here's the warm ones where they have really wet. And then the colors are sizes. So Mercury, Mars size, Earth, super Neptunians, and Jovians. And what I want to show here is like this rectangle where you have terrestrial planets with the right amount of the right amount of radiation that can have liquid water. And so as far as warm Earth, we have 22, but we have 55 in total that were in 2018. And so here are the best candidates to be habitable. Here are the solar system planets in designs. And here you can see that there's Proxima Centauri. Proxima Centauri is the closest star to Earth. It's a small star. It's red dwarf, but it has a terrestrial planet in the habitable zone. All these planets are in the habitable zone. And I'll talk a little bit more about the TRAPPIST. Okay, so stellar activity. So I'm going to start getting into my field of research. So stellar activity in the form of spots, flares, mass ejections, and also affect the habitability of planets. We know that as the star grows slow, it rotates slower due to the loss of angular momentum by a stellar wind. And then the dynamo decreases, its activity decreases. So what you see here is the light curve that is the brightness of the star as a function of time in days. And you can see that a young star, 50 million years, will have very large spots, and that will have a modulated amplitude of modulation, much larger than a 5 billion years old star like the sun. And here's an intermediate one, is 2 billion years. So that's what we expect to see.
How do you distinguish between the solar system planets?
Oh, no, okay. These are on the scale of the rotation of the star. So, I mean, the stars will have like rotation period of 4 to 3 days rotation. The sun, it's about a month, 7 days rotation, the rotation period of the sun. The transits, it's usually totally downwards, never upwards, and the duration is a few hours. like for the further away planets, maybe 10 hours. Usually for the hot planets, the other ones that are very close to the star, it's usually 2 to 3 hours. And the signature is cube-shaped. Because, the orbit, let's say, of the planet, let's say it's like for the fast was like 6 days. So you have 6 days. I think that will last for a few hours and then 6 days. So you can easily distinguish between. So spots very quickly. We know the sun, this is a solar image. We know the sun has spots, and the spots are concentrations of high intensity magnetic fields on the surface, and which, like strike the convective motion. So they're dark. They're about 1,000 to 1,500 degrees cooler than the rest of the atmosphere. Of course, we cannot detect them like this on stars, but we believe that, especially for the solar-like stars, they also have spots. So there are 3 ways to detect solar imaging, just from the modulation, the photometric modulation, because you know that what's causing the modulation are the spots that are, the spots are fixed to the stellar surface. So as the star rotates, more or less spots come into view, and so you have this decrease. And then this method, which is from transit mapping, that I invented. I was the first one to publish this in 2003. And this is basically it. We have the transit, and when the planet crosses in front of a star on the surface, in front of a spot on the surface of the star, in small ball. This is our new images of the sun with simulations of Jupiter size, and at our size, we can't even see the planet. It's smaller than the dash line. And this is what you see for a Jupiter line. Of course, the smaller the more structure from the active regions you can see. Generally for this year is 10,000 times less than this step. Okay, this is the model that I developed with computers, like a pixelated 2D darkened star. And you can add moons and rings to the planet. You can add spots and faculae, which are bright features on the surface of the star. And I'm not going to go into that, and here are some of the papers. About 15 stars mapped, which had its surface mapped using this model. Okay, space weather. We know that the solar activity affects us, like a highly technological society, and the radiation and mainly the particles that are ejected, in periods of maximum solar maximum activity. And right now, this is a year, so 2024 and 2025 are years of solar maximum activity. And of course, it can cause satellites to orbit its orbit due to increase of particle density in air. Geomagnetic storm, which is when our magnetic field goes haywire and we can't, compasses don't work anymore. It affects the ionosphere and long distance radio communications, and cause spikes of electric currents in transmission lines, like power grids. And then, of course, if you have like a spike of current, then what we'll see is and of course, you might lose a signal, like cellular signal and all of that. So as a degree, increase in the ozone hole, the beautiful auroras, and a more controversial thing, which is the influence on the climate of Earth. On exoplanets, we don't know if they have high technology and artificial satellites and cell phones and stuff like that. But we know that they have an atmosphere. If the planet has an atmosphere, the ultraviolet intensity increase due to flares and mass ejections from the star, and strong winds can cause erosion of the atmosphere and, of course, affect habitability. Let's not forget that most of these planets due to observational bias, are very close to their star. So all these activity, it's going to mean much more on this. And well, just mechanism, like stellar wind, you have ions, that will drive the particles of the atmosphere away from the planet, and you have the intense ultraviolet flux from the star, which will cause photoevaporation of the atmosphere. Of course, during this ice planet, the magnetosphere, the magnetic field, can help prevent a little bit, like the mass loss of the atmosphere. And this is just an illustration of how we could detect the atmospheric evaporation due ultraviolet light. So this is what the optical observation letting out of the transit, and this is what the transit will look like in the ultraviolet. Basically, because the planet will have a comet-like structure, the atmosphere will have a comet-like structure because it's being blown away from, like, for instance, the photoevaporation. And here is a simulation, actually not a simulation, these are observations for the star HD20945A, which had the first detected planet in transit. And you can see how the ultraviolet transit, it's much deeper. Well, it doesn't have the optical one, but it's much deeper than the optical one. That was the illustration of here's the stellar winds, and here is Kepler 11, 5 planets. The closest planet, the further away, the red points are simulations, particle simulations. So the red points are particles from the star, and the blue points are points from the planet atmosphere. And you can see how the closest planet is the star is. You can see how the planet is losing its atmosphere. Mass ejections, also MHD simulation. These are from Aline Pidotto. And which is now in Leiden University. And it's a simulation showing also, like the effects both accumulated up. I mean, here's just the wind, here's just the flare, which we could talk about. Here's just the particle ejection of mass, particles from a mass ejection. And here's a combination of both, and you can see the loss of mass in all the cases here. And the coronal mass ejections from stars have been searched for many years. And this is actually the first detection in H alpha from Christian Vida et al. 2016. And what you're seeing here is 11 alpha in blue shade. So that means that there is material, and this is time. Okay, this is time. So you can see that there is material coming towards us. It might be something that thing is stronger than here is most of the side, and then these are interpreted as from the was ejected from the star, from this star here, which is coming towards us. Flares. Okay, so Mackenzie et al. In 2012 from data from Kepler satellite detected this huge effect had been detected before, but because Kepler had such precise observations, it was a space mission which observed the same about 200 stars, 200,000 stars for almost 4 years. So it was easy, not easy, but in the data there are many flare stars where you can see this huge spikes here, which increases 0, so it increased by 8%. The brightness of the star, and these are super flares. Okay, so they are flares which are about 1,000 to 10,000 times more energetic than solar flares. And here's what these super flares that were detected, and here's the largest solar flare that is common in middle flare. And they all seem to follow, like the same distribution. This is flare frequency as function of energy. So apparently the super flares that we see in other stars are just higher energy parts of what we have on the sun. So the ultraviolet do superflares. So it can have both positive and negative effects on the Earth. Because I mean, the positive ones is that for the initial molecules or the precursor of the RNA, other organic molecules, you need a little bit of energy, which the ultraviolet provides. But you don't want too much ultraviolet radiation doses, because of course that will kill the life that is trying to evolve. And the young sun was about 25% less bright than it is today. So here are 3 papers that I published. These highest was my graduate student. She did her master's and doctorate with me. Right now, she's a researcher at JPL NASA Lab in California. And so this was part of her thesis, which won the IAU Prize of Best. The IAU is the International Astronomical Unit. So she won the best thesis award. And this was just part of it. She had a lot more stuff in there. And then we have some people.
I say that we make our minutes over.
No. And Victor, who is currently my graduate student and has a capacity fellowship, and he's going next month to spend a year at JPL. And at the end of the talk, I'm going to talk about his work. So these are the impact, the biological impact of superflares on planets in the habitable zone. 3 systems. Kepler-96, a satellite star, TRAPPIST-1, very small red dwarf, and Choice 700, a red dwarf, not so small, but still. So I'm going to talk a little bit about what we did there. So again, as I said, the superflares, of course, will increase by a lot the amount of ultraviolet radiation. And depending on the amount of radiation, it can cause lots of molecules from the atmosphere, alter the chemical composition of the atmosphere, and even destroy the ozone layer. So our main goal was to determine if these superflares can harm or not to the planet or to any bacterial life that exists on the surface of these terrestrial planets. 26 has an already super. Anyway, it's way too close in, so it's not habitable at all. But we did all the calculation for a hypothetical Earth-sized planet in the habitable zone, because Kepler-96 is a white star, very, very close to our sun. And then I said the TRAPPIST-1 system has 3 planets in the habitable zone, and Choice 700 has 2 planets in the habitable zone. And the outline of the calculation is the following. We detect the solar flare in Kepler data. We estimate what this is optical. So we have to estimate, well, from this energy of the super flare, what fraction of it came out as ultraviolet radiation. And for Kepler-96, it is the sun, the strongest way detected for the sun. And for TRAPPIST-1, we use a similar star, 88, which had a lot of flares detected in ultraviolet. And then for Choice 700, we use a model. And then the atmosphere, you basically consider 2 models. An Aryan atmosphere when there was no oxygen, so that was before the great oxygenation event. So both are atmospheres that are under the Aryan and the present one with ozone. Of course, because the ozone will filter most of the ultraviolet radiation. And then we estimate after there was a flare, we estimate what is ultraviolet plus. We look for 2 different models of atmosphere, how much of this ultraviolet radiation will go through the atmosphere and reach the surface of the planet. And then consider 2 bacteria. Escherichia coli is a common bacteria which we have in our guts. So It only survives in a human being would also survive it. And they cause a radiodurance, which is the most, it's an extremophile, which is the most form that we know that can resist very high dosage of X-rays, so ultraviolet. Okay, so here this Kepler 96, because Kepler 96 is about 2.2 billion years old. And here on Earth, that's when the great oxygenation event occurred from the first algae in the oceans, which produced the first increase in oxygen in our atmosphere. So in which before we only had unicellular life, and then after that we had multicellular microorganisms. And so let's consider what was the end of the primitive Earth, looking what Kepler 96 produced. So Kepler 96, these are during transits, but as you can hardly see here the depth of the transit because of the full intensity here. So these are 3 flares. This one is a super flare, okay, with 10 to the 35 ergs. The largest solar flares are 10 to the 32 ergs. And here is the American hemisphere, 80%, and this is the modern Earth, 80% nitrogen. And then the difference is here. The Arctic one was 20% CO2. The modern one is 20% oxygen. And the strongest flare that we detected on, the bottom area, with all the satellites here on Earth, this is from the sun. Okay, so this time the sun produced a major solar flare, and 20% of that flux came out as ultraviolet. So, and the sun was 75% less bright than it is today. So this is on the surface of that hypothetical Earth-like planet in the habitable zone, Kepler 96. This is what they use. This is just ultraviolet. This is the ultraviolet spectrum. So this is what's the normal flux of the star can be, and this is the increase due to the flare, the highest flare. This is the planet has a present Earth atmosphere. This is how much would reach the surface, and then during the flare, this is how much. And for the Arctic one, without the flare, and you can see that during the present atmosphere under most of the ultraviolet flux will be absorbed, but not for the Arctic one.
The spectrum seems very flat. Okay. That line
It's just 200 meters.
Oh, okay. But do you also get X-rays, or they'll get up to X-rays?
Yeah, because yes.
Yeah, X-rays.
Yes. But you are just looking at ultraviolet. Yes, they will identify spores, hard to left, more injury rates. I was seeing surgeries of those. They're not really good what the injury. I mean, what the hospital. But I know that they have surgery, maybe they found something. I don't remember. Sorry. Okay, so let's calculate the impact on those 2 bacteria. This is the maximum flux, 550 joules per square meter. That's for 10% survival of the bacteria. And of course, Escherichia coli, this number is much smaller, 22. So 550 to 22. That's how much ultraviolet flux these bacteria can receive through survival. And here are just the results. Oh, just forget about this. No atmosphere, of course. Nothing could survive if there was no atmosphere. But then here's for the Arctic atmosphere and for the present day atmosphere. So we have this for that largest flare, and then these are for the smaller flares. But this one, this is for Escherichia coli, and this is for the Enococcus for with an Arctic atmosphere with that large flare, it would sterilize the surface of the planet. Of course, it has oxygen layer and bacteria at bottom. And well, it's just for the smaller flares, and Enococcus could survive, but not Escherichia coli. Okay, we know if the sun was like Kepler-96, it produced such large flares when the sun and Earth were about 2.2 million years old. Survived, right? You know that the single cells went into multi-cells and then into all the evolution until we came to Homo sapiens. So I said, well, we know that we survived. I mean, life survived on Earth. So what happened here? Okay, well, maybe at the time of those giant flares, super flares, life was actually evolving in an ocean or shallow lake, whatever, that had water that could filter. Since there was no ozone layer, there was no oxygen on the surface, on the atmosphere yet. So how did life survive then? How did those organisms survive? Well, maybe there was, maybe we know there was an ocean and we know there were shallow lakes. And I think the biologists probably think that that's where life started, actually near the volcano, not volcano, but all at the vents in the bottom of the. So we went ahead and estimated how much of what would be the depth that the bacteria had to be so that there was enough amount of water to filter all this excess ultraviolet flux from the super flare. And for Escherichia coli, the bacteria would have to be below 28 meters of water. Staphylococcus reflux, 12 meters would suffice. Okay, so it doesn't even, this is well within the photic zone, which, okay, there was enough light from the sun coming to this knee depth of water. So within the point, okay, we could explain it if there was a hypothetical planet. All of it. Okay, now the TRAPPIST one system. The difference here is that it's a dwarf star with only 8% of the solar mass, so it's a very small star. So it's also all this. So I'm sorry. We should also use some of that. This is the whole power system. This is the star. Its temperature is only 2,500 degrees. So the star is much less luminous. And so what happened is that the habitable zone is what is closest to the star. And this star has 7 exoplanets, all detected from transit. So that's what's interesting about it. And it also produces flares. It was during the K2 mission, like the extension of the Kepler mission. So a total of 47 flares were detected. And I mean, this is a much smaller. So it's not going to produce the super flare, but it is going to produce flares that are about 100 times, or at least 10 to 100 times more energetic than the largest solar flare. And remember, all the so the impact is going to be huge. So this is the largest hole. Again, we used AD-Leo to estimate the amount of ultraviolet flux of the total, the bolometric, because in Kepler data you see the bolometric flux, so we have to estimate how much of it, not all of that, goes into the violet. And it has 3 planets in the habitable zone, E, F, and G. Okay. And all the planets, the name of the planets is like they get the name of the star, and then B is the first planet discovered, then C, then T, then not necessarily follows the distance to the star. In this case, it's true, but it's really the discovery. Okay, and so these are the 3 planets in the habitable zone. This is the flux of the star. In ultraviolet, again, this is only the ultraviolet spectrum. There are many lines because there are different times within the red one is the peak of the flare, so the maximum ultraviolet flux. And again, you can see the morning or the Archean or atmosphere. So like the water, kind of lot all that. These are the most harmful ultraviolet radiation. Like almost everything. And so here for the red planets, the two bacteria, and you can see if it has ozone, everybody, everything is fine. But if it doesn't, then only they don't have this radioactive could thrive, could survive. Maybe not thrive, but could survive. And all the two further planets. The closest one, E, not even they don't have this radioactive. And if we do the same thing for the ocean, for the water, then we would have, we only need 10 meters of depth. I mean, these flares are not as energetic as the ones from Kepler 96. There have been some recent studies that says that, well, these planets, at least the closest they would be in the atmosphere due to the fluid evaporation from the star. Okay, now for the last one, and this is Victor's work. So we to say that he just submitted to astrobiology. And this is again a red dwarf, but it's 0.4 mass of the sun. And this is 1.5 here. So this is Trappist one is a bit of the sun. I think it's about 7 million years. But it has 4 planets in orbit that you can see. And then you can see, as I said, each was discovered after the low teens further away. So the letters don't necessarily follow the order, the distance, but most cases you discover the closest one before you do the other ones. This is just an interpretation, maybe not interpretation, and now like a picture of what toy 700C would look like. It's very close to Earth. See, that's 1.07 mass to Earth masses, so which is a little bit heavier. And here under the period and the orbital distance. But it is within the habitable zone, and it's also within the ether border of the habitable zone, just like Earth is in the ether border of the habitable zone of the sun. We don't know if it flares. You know, it was observed by tests, I think, for about 1 month or maybe 2 months, and no flares were detected, but that's a short period. Doesn't mean that the star doesn't flare. So, but before we go into that, let me explain to you what is a transmission. Transmission spectrum is one of the things that James Webb, for all that cosmology thing that James Webb also is looking for. But apart from that, in the exoplanet side, the main goal was to determine the composition of the atmosphere of exoplanets. And how does it do that? It does it through transmission spectrum. What is a transmission spectrum? It's you take spectra while the planet is transiting. Why? Because the light from the stellar, from the sun, will cross the planet here, the terrestrial part. It doesn't have to be terrestrial part. It can also be the outer gaseous envelope of a giant planet. But anyhow, you know, like the tip of the atmosphere, or even the whole atmosphere of the planets. But it's other things, of course, the molecules that are on the planet atmosphere will absorb part of the light from the star. And then, of course, you take spectrum from the star when the planet isn't transiting, and then you compare, because you know, oh, I know these lines are from the star. So whatever is different here, or whatever is in absorption, is from the planet. And here, what it does is that depending on the you're observing as a spectrum, like you take measurement of the transit at different wavelength. And it has zero depth because it has depends on the wavelength. And so, of course, why that not is so first of all, you're going to have different sizes of the atmosphere, but also due to the rate of the star, that's not only that. Just remember that you measure different depth. And this is what's here. So here is a wavelength, right? And what you're seeing here is the transit depth for these on Jupiter was 19 feet. And you can see these peaks modeling. You can get the spectral lines of different elements like water. Of course, this is water vapor because we're talking about a planet that's very close to the stars. Water vapor. titanium oxide and sodium, and even a little bit of haze on the top of the atmosphere. And so this is what James Webb is trying to do: determine the composition of the atmosphere of exoplanets. It's not going to be able to detect oxygen on the surface, on the atmosphere of an exoplanet. Not yet. Not sensitive, but enough sensibility. Because the terrestrial planets, the transits are much lower. And I'm just going to show you here what the simulations were for that showing 700D. So we use this model, which it's not ours, it's freely available. It's called Atmos. It's a photochemical and climate modeling for atmospheres. You can do it for planets in our solar system. It has all the entries, and you can do it for other systems. You enter the spectrum of the star, the size of the planet, and it goes and does its magic and calculates, the composition of the atmosphere. So you see pressure, and this is altitude, and this is the mixing ratio or quantity of each element. So these are aerosols, oxygen, ozone, carbon dioxide, water vapor, methane, silver dioxide, and sulfur trioxide. And again, we did it for 2 types of atmospheres: the argon and the mother earth, for 4 pressures. Those are different only densities of the atmosphere. So an atmosphere 1, 2, and then we did 2 cases of incident ultraviolet. We do not have any flares detected, so we do not know. But let's say the flare will increase by 10-fold the amount of ultraviolet. So normal will clear. And this is what the different pressures and different here is this is argon, and then this is red. And what we can see here already is that the argon here has more aerosols than the mother. And this is confusion, but this is the spectrum, the star. But the different model that is flaring and non-flaring, and this is for normal. This is for whatever atmosphere would be an Earth's surface. Here, this is for and these are really normal. But what is interesting is what would the transmission spectrum of this planet look like? So this is. These two, these are really it's just a little bit different than this for the Arctic. And the difference here is that these are flares, and these are no flares. And these are for the 4 pressures, and this is just for 1 part. And so if we look here, the interesting part is that for Arctic, the no flares, there's a formation of haze here, which will protect the planet's surface more than an ozone layer. So it was a very interesting discovery. And this waves is basically from the presence of methane and SO2 on the atmosphere of this planet. So the presence of those 2 material elements or molecules, will produce a haze that will block most of the ultraviolet radiation. I mean, not with the flare. Yes. This is how, the model will give the atmosphere, and then we did the transits because Victor, increase that, improve that eclipse model that I did for wavelength. I only had it for optical, just in wavelength, and then you put it we made it for spectrum. So, we just use Atmos for the atmospheric composition, so that we know where we do the transmissions, the transition, the propagation of the ultraviolet.
So the Atmos model predicts the haze.
The Atmos model predicts the abundance of CH4 and SO2. And then here, see the signal, because it's only at most, like 12 or 14 parts per million. James Webb will not be able to detect this. So these peaks here falling on the surface of the atmosphere, sorry, of the planet is just too small. The signal is just too small, and James Webb won't be able to detect it.
So the fact that you're trying to buy that.
I think we'll have to wait for Ariel. So we did the same thing. Okay, let's see if we add bacteria on the surface of this 2700D planet. And what would this green zone? Here is the efficient biological barriers. That is the how much ultraviolet flux in the light will be processed by the bacteria. The actual spectrum. What we can see is that Escherichia coli will not survive because it's outside of this green zone for an Archean atmosphere due to a flare, which would increase the flux, the ultraviolet flux by 10. But not all the circumstances and even concentrated would be fine. Like even for the 0.5 atmosphere pressure. So things are not too bad for the okay, Escherichia coli. Goodbye, like if there was a flare which increased by 10% the ultraviolet flux. But recent studies have shown River et al. 2020, I forget the year of the paper. Said, okay, well, too much ultraviolet flux is bad, but some ultraviolet flux to start to pay off, like the reduction of the precursors of the building blocks of life, like our RNA. We know that was the Miller experiment, right? Where just start off the things he had to know, like some electrical discharges. So he's like, we need some ultraviolet. The thing is that this work 2700 has it because it's cooler. It has much less ultraviolet flux than what the sun has or had in the beginning. So some flares were necessary in this case to they begin to get the kickoff to start building like the Sean or not the Sean, sorry, the building blocks of the precursor of the RNA. And so they estimate what the minimum flux should be. So here is this is the minimum flux. Any flux below that, I would even appear on the surface of the screen. And for this is where we have that. Well, we could have that for the atmosphere, usually when it starts off with the atmosphere. But we needed this 10 degrees in ultraviolet for life to start. So can't be too much, but it can't be too little. So probably flares were necessary, knowing if this 1.5 gigayear planet is going to start life. Okay. Okay. So I hope passed to you what the research that I'm currently involved with. Of course, besides stellar activity, the solar activity and stuff like that. But all the flares, ultraviolet radiation, and coronal mass ejection, which will always impact. It's the first point where an oxide was detected. Well, this will be more like Jupiter. But I think this time oxide, we don't really know like the atmosphere gold stars. But the thing is that because mean, this is hot Jupiter, so this atmosphere is very, actually not very hot. We're talking about a few thousand degrees. So probably that's why we have Titan on side. Titan. Then, yeah.
Speak about the stars, no? I mean, the distribution of mass, the star, is that a piece of information that you need? There are some stars that are like a host planet with the habitable zone. Is our galaxy special in the distribution of mass with the star, the chemical position of stars?
Well, the part of the galaxy only to large to answer that. You know, like you've heard galaxies, especially comparing to others. I know that we also have habitable zone, a galactic habitable zone. We don't to be too close to the central black hole, or there's large density of stars and red stars, or neither two are. There is also a habitable galactic zone. As far as the first part that you mentioned, habitability from Yashin, Charles Menendez, he's doing a he has some others where he's interested in, you know, and that maybe if you look at the spectral composition of the star, and if it has more abundance of heavier elements, kind of like silicates and like elements that we see in terrestrial planets, then there might be a correlation. These whole the planets that host stars. This is true for giant planet stars that have giant planets in orbit. They have a higher composition of heavier elements. For lower mass planets, it's not so clear. And the explanation is that, okay, think about the Jupiters. Okay, they were further away, and then due to interaction, like torque with the planetary disk, they came spiraling in. Maybe some of them didn't. I mean, there is a gap. I mean, the planetary disk, the protoplanetary disk doesn't come all the way to the surface of the star. The star has a magnetic field, so there is a gap. So that's where most of the planets stopped before that. But maybe some of them were just coming in, you know, like really high velocity, excited and stuff, and just completely fell into the star, and then increase the composition of the star. Or, well, no, planetary nebula. And they have more heavier elements, and so it was prone to form planets, you know, like the rocky core planets around it. And so the higher composition of the star just reflects the original composition of the. So you have these two explanations. But then for the smaller planets, you know, like the stars that have pretty small planets, then there's no correlation with that.
Okay, but the mass of the star, you propose it more few solar mass star or
Yeah, that's it again, because if we go for like high mass stars, they need to show they live less than 1 million years. Then nobody's interested in them. And they're going to explode the supernovae and just completely, you know, like expel any planets that were in orbit. So, you know, but in not only that, but like transits or radial velocity or it's going to be very hard to detect. Because, you know, like the signal is going to be very small. And like tests, after, you know, like the success of Kepler, tests goal, it focuses on nearby. So it's looking into smaller mass stars. They live longer, they're smaller, so it's easier to detect transits and stuff like that. So there's all these observational biases that towards M stars, which are at least half the solar mass and smaller.
You try to measure the difference of emissions. The planets across
across the atmosphere now. Is it not possible at all to just match our star and look at the planet as it's just near the star so that you can look at the scattered light of the atmosphere by itself only be down?
These are good return tests. People are also directed to the spectroscopy of the secondary planet,
Yeah.
which is like when the planets almost behind. So that's also, but of course, then the signal is. I don't have this bright source of light that is shining through the planet atmosphere. But the temperature of the planets are usually estimated from the spectra just before secondary eclipse.
Let's say planet, like we would call it. So isn't the place where most of these stars, I think, all the but that's what gives it more light. I don't go ahead and because of they're still right. That's don't have really any statistics, but just don't have a for star and you're that pretty much anywhere else. You're stable.
I don't remember. Planets on stars and little clusters. And we can answer that question. Exoplanetas.au. From here, but of course, it also goes to the site. I like this. And then here, selection, Michael Lindsay. Oh, to the side. Yeah, all of them. It's the same number as yesterday.
Yeah.
Doesn't have to be that way. But you know, so it's still almost a different thing.
Yes. You know, the magnetic field is important to protect the atmosphere. And the software levels. What is the assumption? That's the best assumption of the cover the atmosphere.
Oh, which model we used?
Yeah, I think the magnetic field.
No magnetic. No magnetic field. That's just too complicated.
I don't think
Well, we just basically use the composition of the atmosphere, and that's what's it? 80% nitrogen, N2, and 20% CO2 for again, and 20% oxygen for modern Earth. And we got those. I mean, there's a paper by Knudsen et al. Described. I mean, that has all these calculations. But for the Atmos, for the last one, we don't have to do nothing. We can just calculate, based on the flux of the star and on the mass of the planet, what its secondary atmosphere would be. And it looks, and those compositions, I mean, not only, but as a function of height, or pressure. Those maps that I, not that, those plots that I showed with aerosols, methane.
So, but it must be a status of sources.
Yes.
Basic question. At some point in your presentation, you said that it's necessary that the planet has about 1 billion years of stability, so life can emerge. So how exactly do you estimate the age of the planet? I suppose it's
Also, wait, the age of the star,
yeah,
which is very precise.
which yeah, exactly.
Very, it's just an error like this.
That's what.
I mean, except if you have astroseismology instruments, then the age size will not represent. But otherwise, and we don't know the age of, I mean, it's just like our solar system. We
Yeah.
assume that everything holds together, so the age of the stars will be the age of the planet. But then we have to, I guess, the most common way to determine ages is isochrons. Right, but it's very precise.
Well, that's there again. With an announcement of a school that is in Chicago today about exoplanet.